Hello and welcome to the tutorial of oscillators. So today I'm going to discuss with you the way the oscillator works. Now we'll start with some of the basics of oscillators and then we'll go ahead as and when we'll deal with it in greater details. So we'll introduce oscillators as a circuit which is used to generate AC voltage at the output but without using AC input signal. So we actually do not have any input as in fact any AC input as input to the oscillator. However, we definitely get the output in terms of AC. So oscillator is such a device. It is one of the those very few feeble devices which are there in the world which does not accept any AC input, and but we do definitely get some AC output out of it. So let us describe it in bit detail. It is one of the most basic device used in electronic and electrical measurements. Uh, we use most of the times this device for measuring a lot of parameters. Whether we take into account electrical or electronic equipments, we generally most of the time make use of this device. Its key application is in communication system. Now this is one era which we use. The other era is basically used in communication system, where we design a lot of different devices which we basically use for communication. For example, in amplitude and frequency modulation, there are different type of modulation schemes. One of the popular modulation scheme is frequency modulation and amplitude modulation, within which at the receiving end, in dealing with super heterodyne receivers, local oscillators are used to convert incoming signal frequency to a lower intermediate frequency. Now here, many a times we are tend to hear about this as local oscillators. Uh, it's pretty obvious, fundamental, and when we deal with particularly receivers, when we try to receive some data at the output, then typical receivers will basically use typical receivers. They use intermediate frequency, right? Intermediate frequency. I'm sorry. So intermediate frequency, and while doing that, they will basically use local oscillators to generate the oscillations, to generate the frequencies corresponding to the required carrier signal. So sometimes we definitely use these devices to basically uh, look for generating such kind of signals, which helps us to receive, to revive the original information signal back in the receiving end. So this is one of the applications. Now next, oscillators are also used to generate radio frequencies carrier signals. So not only at the receiving end, but they are also used to generate the carrier signal at the transmitting end at the time of while doing modulation. Now we very well know that modulation involves embedding our modulating signal into the carrier signal so that it can be transmitted further. Now other applications of oscillators are in digital electronic systems, where we require a kind of relaxation type of signal, relaxation oscillator, the signal which is generated by relaxation oscillator, which is typically a square wave signals, where we would like to use that square wave to be given to the some sequential circuits so that they will try to synchronize themselves based upon that particular signal, synchronous signal. So they are sometimes used to generate clock signals as well. And now that type of oscillators are called as relaxation oscillators or non-sinusoidal oscillators, as we are going to deal with it later on. Now, as sinusoidal signals are more prevalent in electronic measurement, hence oscillators are most popular signal generators. Now, we tend to use signal waveforms which are sinusoidal quite often in day-to-day life, and that's the reason why we try to focus on most of the time generate these signals, uh, which will basically help us to be used at various places, specifically at the time of measurements. For example, we may take a very casual example of a typical frequency generator circuit. You know, there are FGs. I'm sorry, this is pretty going over there. FGs, which are function generators. Now function generators are used to generate different type of waveforms corresponding to different frequencies. Using them, we can be able to vary the frequency as ever whatever we want. We can be able to vary the frequency, and we can be able to also vary their amplitude, as well as we can be able to get different type of waves. I mean, sometimes we tend to get square waves, sometimes we tend to get triangular waves, sometimes we tend to get sawtooth waves, something like that, right? So I mean, it depends what kind of waves we are targeting for. And then most of the times, I'm sorry, this is something which is unnecessary, but we'll see how to do it. So sometimes we also use to generate a typical sinusoidal wave out of the function generator. So all in all, that is the best application we can ever think of corresponding to an oscillator. Now, oscillator converts unidirectional current from a DC supply to alternating current of desired frequency. Now we have already said that generally oscillators are not used to have any inputs. When we speak any input, then that means that it is particularly the sinusoidal input. So we do not have any an alternating signal input in case of oscillators. But however, it's pretty sure that we will definitely be getting the desired frequency, which is alternating frequency at the output. So I mean, all in all, we can say that it basically converts a unidirectional current, which is in the form of DC, which we are going to see just now, into the form of an alternating signal. So its function is reverse to that of a rectifier, where we already know that rectifier is used to convert a typical AC to a corresponding DC signal. So it is just opposite than this. So generally, oscillators are supposed to provide AC voltage signals. Now, let us try to compare and contrast the two, that is amplifier and the oscillator. Now, typical amplifier looks like this, where it tries to revive the input digital signal, which is of low voltage. You know, here we tend to get input digital signal which is of very very low voltage. It is in typically millivolt range, okay, not more than that. And in order to amplify this signal, so that it can be able to, you can be able to get much higher amplitude of this signal, naturally keeping the frequency same. uh, we try to have additional power which is generated by a corresponding DC power supply, that is DC uh, power input. So using this DC power input, which is acting as a source to provide additional power to be given to this input signal, so that as a result of that, by these two, I mean, we know that by using the concept of biasing, we can be able to provide the additional power via biasing to an amplifier, so that the amplifier will, as a result of this, gives us the most prevalent, most perfect output. So now, okay, let's go ahead with the things. Yeah. Now, contrasting to this, we have something called as oscillator. Now, in case of oscillator, amazingly, we do not have any input which is AC, alternating signal. You can see there is no alternating signal which we are giving as an input. So there is no alternating input here, which we are receiving. However, in spite of that, we do have as usual DC power input which we are supplying from the other end, and we are getting the signal output as a result of that. So amplifier generates output with the same waveform as that of the input, but its power level is very high, so the additional power is supplied by the DC level. So in case of amplifier, the additional power is supplied by the DC level, but then at least it has the similar waveform which we are trying to get at the input. Which we are putting at the input to be amplified at the output. But here, oscillator is a device which produces AC signal without any input signal. Now this is something which is very much amazing. Without any AC input, we are trying to amplify the output. I mean, by the concept of feedback, which is called as positive feedback. So, I mean, we'll see the functionality in details whenever we'll deal with the next tutorial of oscillators, where we will see the functioning of it, where we'll discuss Barkhausen's criteria and the way it is getting applied to oscillator. There we'll make it very clear that how do we actually generate it. So it keeps producing output till the DC is supplied. So as long as we are having a DC input at the oscillator, yes, we can be able to get the output in terms of AC. Okay. However, the mechanism which is involved over here is that the alternating tendency which we are trying to receive or revive at the output, we get from the noise. Now this is the only circuit which is in which we are trying to use noise for our benefit. So what we are doing, we are trying to apply positive feedback to the existing noise which is there within the oscillator. I mean, noise is omnipresent. I mean, we always have the fact keeping in mind that we should keep this thing in mind always, all the time to come, that noise is everywhere. Only thing is that for all other cases we try to suppress it because it is acting as an undesired signal. But then this is the only place where we would like to preserve it so that it will give us the specific alternating waveform or alternating look outlook to the signal. So that alternating tendency we try to derive out of the noise, and that's how we'll try to convert a DC input to an alternating input. Okay, so that's the logic behind it, or that's the secret behind it. That why it produces. See, I mean, it's very easy to compress AC into a DC in case of typical rectifier, but however, it sometimes feels very difficult to imagine that how can a DC signal can be able to. I mean, how can it can be able to convert it to a particular AC signal? So this is how it gets converted. Now, oscillator does not require any external signal to start or maintain energy conversion process. Now, this energy conversion process um, is fully automatic. I mean, as I told you that it involves the concept of conversion of noise to corresponding uh, alternating output. So, therefore, it doesn't require any external source to feed in. So apart from DC, there is no other external source which we require in case of oscillators to generate the alternating output. Now, generally we classify oscillators in different types. So the two prominent types of oscillators are sinusoidal oscillators and non-sinusoidal oscillators or relaxation oscillators. Now, first we'll discuss sinusoidal oscillators. So sinusoidal oscillators are the oscillators which produces output having sine or cosine nature. So we typically, these are the most popular oscillators which we ever use all around the world, because the sinusoidal waveforms are the most basic waveforms which we generally use in all the signal processing applications. So they produce waveforms in the frequency range from 20 hertz to 20 gigahertz. Now that is the range which is supported by sinusoidal oscillators. Now next comes the non-sinusoidal oscillators or relaxation oscillators. And as we discussed in one of the applications earlier, that in case of digital sequential circuits, we do require some waveform which is called as clock waveform, and then to generate clock waveform, we require some kind of oscillators which are also called as non-sinusoidal or relaxation oscillators. So these are the oscillators which produce output waveform which are square or rectangular or sawtooth waves in nature. So you might have seen these things on the function generator. When we deal with function generator, then there is always an option provided by the function generator about the type of waveform which we are trying to get. We can get a square waveform out of it. We can get a triangular waveform. We can get sawtooth. We can get sinusoidal. Whatever we desire, we can be able to get it easily from that. So that's how the next application of oscillator. I mean, next type of oscillator. In fact, it's a relaxation oscillator, and using this, they can be able to produce the frequencies from 0 hertz to 20 megahertz. So sinusoidal oscillators can be further subdivided into following types. Now we do have further subtypes of sinusoidal as well as non-sinusoidal oscillators. However, now let us quickly divide the sinusoidal oscillators. So now there are These are the four typical types of sinusoidal oscillators: tuned circuit oscillators, RC oscillators, crystal oscillators, and negative resistance oscillators. So out of these four, the first three are more popular oscillators, and we are going to discuss them in details in the future lectures to come. In the lecture, I mean, this is kind of a lecture series we are trying to launch, and in the future we are going to discuss more about these things which we are discussing at the basics. So in the next few lectures we are trying to evolve with tuned circuit oscillators, RC oscillators, and crystal oscillators. Now tuned circuit oscillators are something which uses tuned circuit, which basically consists of uh, L and C, that is inductance and capacitance, to generate high frequency signals. You know, sometimes we generally use the inductance and capacitance, which are basically smaller in size, uh, to convert them into, to basically use them to convert into high frequency signals. Because I mean, it's pretty obvious that they are basically related to the the dimensions of inductance and capacitance. More will be the dimensions, lesser will be the frequency. So we definitely want to go for lower and lower dimensions so that it can be accommodated in the smaller area. And that's the reason why we generally use L and C, which are small in size, and then therefore as they are small in size, so we can't expect them to work at lower frequencies. So therefore they generally work at higher frequencies, and they are called as radio frequency oscillators, because RF frequencies are pretty high, I mean, in the megahertz range. So they are also called as tuned frequency oscillators, tuned circuit oscillators. The examples are Hartley, Colpitts, and Clap oscillators. Now, out of these three, I mean, we are going to discuss in details the working of Hartley and Colpitts oscillator in the slides to come, in the lectures to come. The next type of oscillators are known as RC oscillators. Now, these oscillators, as the name suggests, they use resistance and capacitance to generate lower end audio frequency signals. Now, these are the low frequency oscillators which we are looking for. Uh, I mean, because we definitely work on low frequencies as far as voice is concerned. So, they are basically the audio oscillators. So, they are called as audio generators, audio frequency generators. For example, now the examples includes phase shift oscillator and Wien bridge oscillators. So these are the two examples of RC oscillators. First one is phase shift, and other one is Wien bridge oscillators. Now these are also the oscillators which we are going to discuss in details as the time will come, as the as we go ahead in the topic. Now, thirdly, we do have a crystal oscillator. When see crystal oscillators are used at those places where the stability of the frequency counts a lot. I mean, it is see it's not important to generate just generate the frequency continuously from an oscillator, but it's also important to maintain it particularly at the same frequency level all the time for all time to come. So sometimes it's not so easy. Let's say we are getting some frequency out of oscillator, and then sometimes see things keeps on changing. I mean, the values of the components also sometimes changes with the time as we utilize that component for more time to come. So that way we cannot guarantee the performance of the oscillator to be producing the same frequency continuously for all time to come. So that basically gives you the idea about the stability of the oscillator. So as far as the stability is concerned, now that is going to be the best option, which is known as crystal oscillators. So now crystal oscillators are basically consisting of quartz crystal, and we know that quartz crystal are highly accurate as far as their performance is concerned in the long run. So therefore, these oscillators are very much utilized at those places where the uh, particularly the concept of stability of oscillations which are getting produced, or stability of the waveforms which are getting produced in the long run, is important. So it is, these oscillators use quartz crystal to generate highly stabilized output. Now this point over here is worth mentioning here as highly stabilized output. So whenever we will want to go for highly stabilized output signal, then definitely we would like to prefer the crystal oscillators with frequencies up to 1 megahertz. So we can be able to generate 1 megahertz frequency. The example of this is Pierce oscillator. Now next is negative resistance oscillators. As we very well know that one of the important diodes which basically works in the negative resistance region is tunnel diode, and using that we'll try to make an oscillator which is known as negative resistance oscillator. So they use negative resistance characteristics of the devices such as tunnel diode Tunnel diode oscillator is example of negative resistance oscillator. So this is another type of oscillator. Although we do not utilize this oscillator much into the practice, uh, in practice most of the time we'll be basically looking for tune frequency oscillators, RC oscillators, and the crystal oscillators. So now what are the applications of sinusoidal oscillators? Now let us come back to the sinusoidal oscillators, because we have seen that these are the types of sinusoidal oscillators which we have seen just now: tune frequency oscillator, tune circuit oscillator, then RC oscillator, and the crystal oscillator. So what are the applications of sinusoidal oscillators? So as we have discussed, sinusoidal waves are the basic waves which we very well utilize for all communications all around. So they have a variety of applications in telecommunication, where sine wave is used as a carrier signal in both wire and wireless transmission. So we very well know that sine wave is a very important wave, which is we can say very basic building block of all the waves. I mean, if you study Fourier transform, then we'll see that we can be able to generate every wave. I mean, every wave in the world can be made up of sinusoidal waves. So sinusoidal waves and their other what we can say uh, other related frequencies out of it. So sine wave signals are also used in testing frequency response of the various electronic systems as well as um, equipments. And the examples includes we can be able to test amplifiers, filters, and analog communication channels, etc. Now these are the applications of sinusoidal oscillators. Now what kind of sinusoidal oscillation basically can be produced out of it? So there can be two types of oscillations. One is known as damped oscillation and other are undamped oscillation. Now damped oscillations are typically looking like this. Damping here means that the amplitude of the oscillation goes on decreasing with the time. So electronic oscillations whose amplitude goes on decreasing with time, they are called as damped oscillations. So here we can see here that the amplitude is basically following an exponential decrease as we go ahead with the time. So if you follow this, then you might observe that there is an exponential decrease as we go ahead, and so also we'll feel that this exponential decrease is basically pertinent over here also. So whenever we deal with this kind of damped oscillations, then we say that that is damped oscillator. And damped oscillations are produced in those oscillator circuits in which power loss takes place continuously during each oscillation without any means to compensate for the same. So we naturally say that I mean, we casually see also usually that let's say if you want to use LC oscillator, or if you want to use RC oscillator, we naturally consume energy in both the types of cases. We definitely consume energy, and unless and until we do have some ways to preserve that consumed energy or to revert it back, that consumed energy, I mean, the oscillations are going to be damped in the long run. So therefore, these are those kind of oscillators where we do not have any mechanism to compensate for the loss which we have got in the, while doing oscillations. So those kind of oscillations are known as damped oscillations, but frequency of oscillations remains unchanged as it depends on the circuit parameters. So see, the frequency of the oscillation is always pre-decided as per the type of oscillator. For example, if you want to take LC oscillator, then 1 upon 2 pi under root LC is one of the frequency of oscillations which is getting produced. So as far as frequency is concerned, it doesn't make much difference as far as damped or undamped oscillations, for damped and undamped oscillations. However, but the the power definitely matters. So if you are not able to supply the enough power as the time progresses, then those kind of oscillations are of not much utilized. So, but frequency of oscillation remains unchanged, and it depends on the circuit parameters. Therefore, I mean, frequency is always decided by circuit parameters. Now, undamped oscillations, the electronic oscillations whose amplitude remains constant with time is called as undamped oscillations. So, see, oscillations will only be undamped only when we do have some supporting mechanism to support the power loss which we have basically consumed during the oscillation run. So undamped oscillations are produced in those circuits which will have power losses, but then we do have a compensating mechanism to compensate for the loss of power which we have got, and due to that mechanism, the oscillations will be sustained throughout. the same way as now, as we'll see way ahead when we'll discuss Barkhausen's criteria. Then initially we'll try to make sure that we are trying to increase the oscillations till the time we will reach up to a particular optimum value of amplitude, and as soon as we get that particular optimum value of amplitude, then we'll try to sustain the oscillation. However, while sustaining, we must keep in mind that although we have decided with the frequency, however, the sustenance will always be possible only when we'll supply enough energy at the input of the oscillator, so that the oscillations will be maintained of the same amplitude. Now, next is as we very well know that oscillations can only be produced by amplifying the small undesired signals, which are called as noise signals. Now, when we say like this, then definitely we would like to use a concept of positive feedback, which is basically a basis for oscillator. So positive feedback amplifier is basically forms the basis for designing an oscillator. Now, negative feedback, we have very well know that it is very much utilized to design the amplifiers, and we have seen that there are a lot of advantages of negative feedback rather than positive feedback. So, because one of the advantages is that it brings the stability of the to the amplifier. However, we do use another feedback, which is positive feedback, to design one circuit which is called as oscillator, and this will give us sustained oscillations for all time to come. Oscillator is a device which generates AC output signal without any AC input signal. So now this we already revived this statement earlier, that oscillator does not require any AC input. Now a fraction of the output is fed back to the input, which is in phase with the input. Now this is the typical characteristics of a positive feedback. Now this is what we actually do in positive feedback. So in positive feedback, we try to feed some portion of the output back to the input in the same phase as we are taking the input. So this will give us the this is basically derived from the positive feedback. So feedback signal is only input to the feedback amplifier, and we know that the closed loop gain of this positive feedback amplifier is given by AF is equal to 1 A upon 1 minus A beta. Now this we have already derived it earlier. Hopefully we will be able to record those lectures as well, where we have derived the expression for different type of feedbacks, positive as well as negative feedback. So here you can see over here, A beta is basically loop gain, beta is feedback ratio, and if now let us make this A beta factor equal to 1 in this case, and now if you put it 1, then we'll see that AF will become infinite, because A upon 0 will be infinite. Now here we can be able to generate output without the input. Now infinity means that we even if we do not have anything as an input, still we are going to generate output out of it. So therefore, if you keep A beta equal to 1, we can be able to get sustained oscillations. Now oscillator is an amplifier without any AC inputs, but it operates on the principle of positive feedback to generate the AC signal at its output. So that's the way we say that without any input also we can be able to generate the output out of it. So an amplifier can work as an oscillator if the positive feedback is made to exist. So if you can be able to get the positive feedback within an amplifier, then the typical amplifier circuit, which includes amplifier and the feedback network, will basically be converted to an oscillator. Okay, because see, usually the amplifier circuit consists of two things. One is I mean, particularly speaking, negative feedback amplifier, we do use one amplifier and the oscillator. I'm sorry, we do use amplifier and the feedback network. So if we somehow try to get the positive feedback out of these two components, and uh, then we can be able to generate the oscillations out of it. So, but positive feedback will not always guarantees oscillations. Now, although we say that positive feedback always gives us the way we wanted, as we have seen earlier, that yeah, I mean, this is the way we can be able to get the output AF as infinite. But however, this is not the only way to get the oscillations. An amplifier will work as an oscillator only if it satisfies some set of conditions, and these set of conditions which are somehow highlight in the form of criteria, which is called as Barkhausen's criteria. Now this is one of the important criteria to be remembered if you want to learn the oscillators. So oscillators are basically based on one very important criteria, which we always say that it is Barkhausen's criteria. Now, what's this criteria is all about? Let us try to see. Barkhausen's criteria states that the oscillations are sustained only if the magnitude of loop gain will be unity and the loop gain phase shift is zero. So there are two things now here which is coming into picture. First thing is that the condition, there are two conditions over here. One is basically related to one is related to basically magnitude response and other is phase response. So as far as magnitude response is concerned, the loop gain magnitude must be equal to 1. And the second thing is that phase shift. Now there should not be any phase shift within the loop. As I told you that there are basically two loops in any oscillator, or in a typical amplifier. A negative feedback amplifier does have two loops. This is the first loop which we basically use for amplification, and this is another loop which we basically use for feedback. So all and all we would like to say here is that in using these two loops, we must make sure that there should not be any phase shift between the two. So the moment we are giving the input over here, the signal, the phase of the signal which we are giving over here should be able to return into the same phase. So there should not be any phase shift for the for the signal uh, throughout the loop. And then the second condition is that the modulus of loop gain, which is a beta, must be equal to 1. So these are the two conditions which will give us the condition for generating the sustained oscillations. So on putting a beta equal to 1 in the expression of positive feedback, gain of the positive feedback, we will do realize that AF will become infinite. So when closed loop gain is infinite, now we can be able to say that we will be getting the output signal without any input signal. So to generate the oscillations, in fact, we usually do not keep it 1 initially. However, we keep it more than 1, greater than 1 initially, so that at least we can be able to generate some amplification, some waveform by using a continuous full value of positive feedback. We can be able to at least develop it to a greater extent. And now we know that noise voltages are so small in their stature. They are having a very I mean millivolt range sometimes, and even microvolts also sometimes, some other times. So first of all, we would like to amplify them, and we will try to nourish them. We will try to make them suitable for our oscillation internally. So initially we would like to keep the loop gain a beta greater than 1, and as we have achieved that, then it should be kept greater than 1 initially, and then this will basically amplify the oscillations to a great extent. And then we'll see after a short while that how it is used to amplify that initially. I mean initially the noise voltages are of very small amplitude, and as the time progress ahead, we'll try to get the amplitude much bigger, and till the time we get the required desired amplitude, we'll try to apply the condition of AB greater than 1, A beta greater than 1, and then once we'll attain that particular uh, amplitude, then we'll keep the A beta equals to 1. So therefore the condition stands to be mod A beta greater than or equal to 1. So initially greater than 1, and then once we'll attain that particular amplitude for oscillations, then we'll keep it 1. So that is, it should be kept greater than 1 initially and to give rise to oscillations, and once it gets generated, then it should be kept at some magnitude, same magnitude, that is a beta equals to 1 for basically maintaining the sustained oscillations. So there are two conditions which it maintains. First condition is a beta greater than or equal to 1, greater than 1 for initial phases, and then it becomes equated to 1 for the next phase. And then next criteria is the phase shift around the closed loop should be equal to 0. And that's the condition for a typical condition for positive feedback. So this condition is pretty obvious because we are going to use positive feedback in our oscillator design. So now we all know that this is one of the important conditions for feedback to be positive. So these are the two things. We can see here amplifier and the feedback network, they are having zero phase shift. So we could say here that amplifier will always generate 180-degree phase shift. I mean, no doubt about it. Most of the amplifiers will generate 180-degree phase shift. So if you get 180-degree phase shift somehow out of the amplifier, then it is very important for us in case of oscillator to generate another 180-degree phase shift over here. So we should be able to generate another 180-degree phase shift, which is generated by the feedback network compulsorily, so that all and all, when we'll add both of them together over here, because here Vi will become equal to uh, Vs plus Vf. So here Vs will give you 180-degree phase shift and Vf will give you 180-degree phase shift. So both will, when both of them will combine together, then all in all we'll get a total phase shift of 0 degree, because it is nearly equal to 360 degree. So this is the first condition for oscillations to for the oscillator. And then the second condition is that the magnitude of this term A beta must be greater than or equal to 1. So loop gain must be kept greater than or equal to 1. So now let us see. So these are the two conditions which are very important conditions, which will basically give rise to the oscillations, and these two conditions are basically called for Barkhausen's criteria. Now effect of mod A beta on nature of oscillation. Now here we would like to see how the mod A beta affects the oscillations. Now there can be three possibilities: either it can be equal to 1, or it can be less than 1, or equal to, or it is greater than 1. So when it is equal to 1, then we will get sustained oscillations of constant amplitude. So as you can see over here, corresponding to A beta equal to 1, we'll get a sustained oscillation. In case of A beta greater less than 1, here the feedback signal is in the absence of signal generator, which will not be sufficient to sustain the oscillations, and then hence the output will go on reducing exponentially. And this was the usual case. Usually this happens when we do not have any compensating mechanism set for sustaining the oscillation. So therefore this is what it happens. So you can see over here the output is exponentially decreasing as the time will progress ahead, as we do not have any sustenance mechanism, and therefore the output goes on reducing as the time will progress ahead, right? And the next thing is A beta, mod A beta greater than 1. So when we'll do that, then total phase shift around the loop of the amplifier and phase feedback network is still 0. I mean, because that's the important condition of positive feedback. Then oscillations at the output will basically rise exponentially without limits. Now this is what is important, and that's how we do in case of oscillators. That initially the noise signals are of this amplitude. You can see here it's very small, but when by the help of positive feedback and by keeping the value of A beta greater than 1 initially, we try to amplify it as far as possible. And once we get the desired amplitude, then we'll stop it. Now, otherwise, it will go on and on and on and without limits. I mean, it may go to saturation. I mean, it may saturate our device over which we are measuring. So we do not want to do up to that extent. But what we want to do is that we'll restrict it at the same place, and then after that, it will be made equal to 1, so that the further oscillations will be sustained for all time to come. So we can conclude that the oscillations will be sustained only if A beta greater than 1 initially, as it is desired, so as so that so as to generate the oscillations and to increase their magnitude at the desired levels, and then to sustain them by keeping A beta greater than 1, A beta equals to 1, so that now the oscillations will be sustained as it is for all time to come. So maintaining the total phase shift around the amplifier and the feedback network to be 0. So this is the lecture which will tell you more about the oscillator in greater details. So further lectures will basically communicate more about different type of oscillators, which are basically LC oscillator and RC oscillator, etc.